Okay, so this is the last review topic. In fact, I used to teach 101 on occasion, and these pictures and next few pages are from that same course guide I had back then. All right, so intermolecular forces. Now, what's going on with intermolecular forces is we're acknowledging an interaction that is not a bond. So in other words, they might make a cluster or an association, right? So these groups of molecules, this is water, for example. We know that water hydrogen bonds, that's kind of a fundamental sort of foundation for getting to this point. But what happens when it hydrogen bonds? Well, it makes this sort of arrangement, and we don't call that a new molecule. It's still a bunch of waters, right? So breaking up that hydrogen bonding does not destroy water. Breaking up a bond between hydrogen and oxygen destroys water. It's no longer water. So when you break the intermolecular force, you're not changing the molecule. So in other words, if you're boiling, which is the process going on here. So in other words, if we add energy to, let's pretend this is a liquid sample of water. And these dotted lines are used to indicate intermolecular forces. Because they're not a real bond, right? Intermolecular force, aka non-covalent interaction. Because non-covalent meaning it's not a bond, but it's still an interaction. They're still attracted to each other. So let's indicate those attractions. Now that we're bringing this all together, we have the shape from Vesper giving us the bent. That's why we need this. We have the dipole. We know water's polar. Let's draw the dipoles. Delta plus for the hydrogens, delta minus on the oxygens, right? These are very polar bonds. Delta minus, delta plus is for all hydrogens. So white ones are hydrogen. Now, if we trace the hydrogen bonds, these non-covalent interactions, we see the plus is attracted to the minus. No surprise. Plus on the electron poor hydrogen attracted electron-rich oxygen. And they intentionally actually line up and make this like lattice, this sort of superstructure, based on optimizing these interactions, right? So when, however, we add heat, which adds kinetic energy and the molecules start vibrating, moving, it actually disrupts these interactions and they separate. So if we add heat is that's our most common form of energy by far. We often abbreviate that delta, by the way, over the arrow. Delta by itself means heat. When it's in front of a variable, it means change in. So I know it can be confusing because most of your math, physics, and other chemistry classes so far will say delta E for change in energy or delta T for change in temperature. And you know, we do that too. But when it's delta by itself, that's actually the abbreviation for heat when it's over the arrow. So that means we've increased the temperature. We disrupt those non-covalent forces. They break that network apart, but they don't break the molecule apart. Water is still water, right? It's just separated. And in fact, we might have some liquid still here, but much of it is going into the gas phase. We often show that with that squiggly arrow going up high. It means gas getting evolved or forming gas, evaporating, right? All right, so this is basically what's happening when we boil. Okay, so knowing that boiling will break up these interactions, who has a higher boiling point? Molecule in pot A with weaker green bonds, or molecule in pot B with stronger green forces? IMFs, we call them, intermolecular forces. Who has a higher boiling point? The one with stronger IMFs, right? So in other words, let's write that trend. If we increase non-covalent interactions, IMFs, that correlates to an increase in boiling point. Okay. All right. Let's put that practice or that trend into action. Let's try to understand why. And to understand why, we get something like a physical observed property changed. The boiling point's different. What intermolecular force is causing it, and why are some stronger than others? So to answer that, we're going to actually target some very specific molecules. So we'll look at water. Let's draw the Lewis structures because structure is going to tell us the function, right? We know that. Water, CH3CO, CH3. That's the condensed structural formula for acetone. And isobutylene. So that's iso group means this, and then we have 4 carbons total. You don't have to name that, but it looks like acetone without the oxygen, which is what it is. It has a carbon, a CH2 instead. Now look at these differences in point. They're all pretty small molecules, but look at the difference. Water has the highest. Acetone, if you've ever used acetone, you can smell it for a reason. It's very volatile. It evaporates quickly. Isobutylene, much lower boiling point. So in other words, negative 6.9 degrees. So in other words, it's harder to evaporate acetone. It's even harder to evaporate water. What's going on? That means that this must have, based on the trend above, if boiling point is affiliated with intermolecular forces, this one must have, since it has the weakest lowest boiling point, must have the weakest intermolecular forces. Therefore, this one must have the strongest intermolecular forces. Let's look at them because we need to know why. To start this off, we'll compare 2 side by side. So let's, instead of all 3. So why does acetone have a higher boiling point than isobutylene? Remember, what makes something have an intermolecular force is an attraction. What causes an attraction are things like partial charges, dipoles. So let's look for dipole. Yep, carbon-oxygen bond, very polar. Delta minus, delta plus. Is there a dipole in isobutylene? No, very nonpolar. So when isobutylene sees another isobutylene, it's like pretty, ambivalent about it, doesn't care, just sees a bunch of other, it really doesn't make a difference. However, when acetone sees another acetone, it's going to line up soldier style, very specific way. That delta minus on the next one is going to be close to the delta plus on the other one, so they can draw that coveted green dotted bond. It's often green, but not always. All right. Oops, I'm going to do the dipole in red though. That attractive force happening right there between a delta plus and a delta minus between 2 polar bonds is called a dipole-dipole interaction, because we have a dipole and we have another dipole. Dipole-dipole interaction. Actually, I'll fill it in here. Dipole-dipole interaction. Right, so nonpolar has no dipole interactions. No dipole interactions. Therefore, it makes sense that acetone has a higher boiling point. Okay, so that's dipole-dipole forces. You might have heard those before. Now, water has a dipole. All right, let's draw it. That gives us that big old delta minus here, delta plus is here. And that explains a lot about why the next water, the oxygens will stay away from each other. They're repelled, and in fact, they're attracted to the other hydrogen. And so we get to draw that green dotted line there. What's going on there? I'm going to draw in lone pairs too. All right, so we're comparing this, keep drawing our dipole, versus our acetone scenario. Now, they both have dipoles, and yet water has a significantly higher boiling point. So let's just look at why this particular interaction is so much stronger. It's an O making a non-covalent interaction with an H, whereas this is O making a non-covalent interaction with a C. Remember good old Fonkel-Berish? Think about H and O versus O and C. So O and C was this scenario. O and H was this scenario. Who has the bigger dipole? OH, therefore the bigger delta pluses. So the magnitude of this interaction is stronger. So this is your simple plain old dipole-dipole interaction, but although you may be tempted to call this a dipole-dipole interaction, it has its own name because it's significantly stronger. This is called a hydrogen bond. And it's so important biologically and in the behavior we see even synthetically that we keep it in its own category. So you got to recognize it when you see it. So this is a stronger attractive force. Hydrogen bonding. It's not a covalent bond. In fact, you want to also not only be able to identify when there's hydrogen bonding, you want to know who is the acceptor and the donor. So the acceptor, who's accepting a bond with an H, is there, the oxygen, acceptor, it's two C's. And the H itself is making the H bond, it's the H bond donor. So it's a donor-acceptor interaction. Okay, so this is called hydrogen bonding. It is limited to O and F. Okay, so this region of the electronegativity scale. So let me highlight it. With H. So when hydrogen is connected to an O, N, or F, that gives a big enough delta En, right? To be classified in that category, to be strong enough, right? So carbon is not invited to that party because it just doesn't make that strong of an attraction compared to H. Okay, you can also, the reason hydrogen bonding deserves its own class and it's not simply just dipole, just a, this definition so far makes it seem like it's simply strongest type of dipole-dipole interactions. And that's true with this example. But there are cases where you might even have full-on charge making a hydrogen bond with a hydrogen. So the atom, in other words, the hydrogen bonds must have a lone pair of electrons and a large delta minus, on a small atom, O, N, or F, or a full negative charge. So that doesn't happen in dipole-dipole because dipole means partially polarized, right? It's completely polarized if there's a full negative charge. That's the hydrogen bond acceptor. Now, in our class, we mostly focus on the hydrogen bonding examples that are dipole-dipole analogs, but they're always only eligible elements are O, N, and F with H. Okay? Solvents like water and ethanol, remember ethanol, that are capable of hydrogen bonding therefore have a special name. They're called protic solvents, meaning they have an available proton to form hydrogen bonds. The fact that we ever refer to a hydrogen as a proton also indicates that it can act as an acid, which is true. Okay, now the last scenario. So let me actually say this is a protic solvent. The last type of IMF that we're going to cover so far is what's got multiple names. Fleeting dipole-dipole interactions, aka, I'm going to write a bunch of AKAs here. Van der Waals forces, depends on what your general chemistry textbook said, but we're going to lump them together. Interactions, aka London dispersion. I like the fleeting name. It's not how I originally learned it myself, but I kind of like it because it's describing what it really is. Fleeting means temporary, right? Doesn't always happen. So pentane, for example. 1, 2, 3, that's butane. 4, 5, pentane versus butane. Pentane has a higher boiling point. Why? Well, that's because there are, even though these are both nonpolar, right? So both are nonpolar. But when a nonpolar neighbor sees another nonpolar neighbor and they're close enough, they can actually induce a temporary dipole. In other words, if another pentane approaches another pentane, their electron clouds will be distorted so that all of the minus charges are far away. So you temporarily polarize. So I'm putting these delta pluses in here. You know what? I'm going to color code that because the numbers are making that hard to see. So I'm going to do delta pluses, or delta minuses up here. And then I'll do some delta pluses underneath. So that pentane became temporarily polarized. It does not have a dipole. It's a nonpolar molecule. But with a neighboring one coming by, its electron cloud shifts so that you don't have any repulsive forces, and the delta minus on one side will interact with the electron poor side of the other one. So it shifts its electron distribution to have a favorable interaction. So those are favorable intermolecular forces right there. So if I draw this out again, and they stack just right, you can have these temporary dipoles allowing them to be attracted. So the same thing happens in butane, but butane is just smaller. There's less surface area. So there's less of it to kind of help stick to each other. Okay, so this is written out in words for you here. Hydrocarbons are made of nonpolar bonds, so a full-fledged dipole-dipole interaction is impossible. So it does not have a permanent dipole, i.e. no permanent dipole. Instead, they experience transient, passing, fleeting dipole interactions, also known as London dispersion forces. These interactions increase, so there's more of them when it's a bigger molecule, so molecular weight, or based on the shape, surface area. Oh, area is already written out for you, okay? So I'm going to describe this here as an induced dipole. The presence of its neighbor induced the dipole in both of them. If the neighbor hadn't come close to it, there'd be no dipole because there's no temporary dipole. Okay, so let's do a couple examples. Stop and think about it. Who has the higher boiling point? 2,2-dimethylpropane. Let's draw that first of all. 2,2-dimethylpropane. Propane's the parent. 1, 2, 3. 2,2-dimethyl. There you go. Versus back to pentane. 1, 2, 3, 4, 5. All right, who has the biggest boiling point? In other words, who has more attractive forces? Well, you're actually going to need to think about this because they have the same molecular weight. They both have 5 carbons. So think of the other reason listed as to what can influence the strength of these fleeting dipole forces.
Watch it lock, boy. Boiling water dancing in the pot. Watch it rock, boy. Boiling water dancing in the pot. That Millie rock, boy. Ugly, but I'm handsome in the yacht. Boiling water dancing in the pot. Watch it hot, boy. Boiling water dancing in the pot. Millie rock, boy. Boiling water dancing in the pot. Watch it hot, boy. Boiling water dancing in the pot. Millie rock, boy. Forever.
Okay, so who has the higher boiling point? Pentane. Did you get that? Since they are the same size molecule, they are both C5s, right? We're going to have the same molar mass. So the size didn't make a difference. But what was the other factor? Surface area, right? Surface area. So let's just pictorially represent the surface area. This is roughly spherical. This is like a big, long oval. So let's draw a neighbor for this one. Spheres, by definition, interact at one point, whereas big, long ovals can have multiple contact points. So more surface area means this has a higher boiling point. So when you're doing these problems, watch out for differences in molecular weight or surface area. Okay, so now we have learned reviewed three dipole non-covalent interactions, the most important ones. We will add a few more later, but these are the major players that since this is review after all. We have H bonding. Remember we said that was much stronger than dipole-dipole. But of course, this is based on permanent dipoles. A dipole-dipole interaction is going to be much stronger than a London dispersion force. Now, this is important for us to understand what we see in the lab. So we go in the lab and we see a difference in boiling point. That's a physical property that's different because of something at the structural level. Now, what about other physical properties? Boiling point's not the only thing affected by intermolecular forces. So I'll summarize some of the others you want to be aware of. So as you increase intermolecular forces, we saw, that was kind of our example we worked with, we increased the boiling point. What else would we change? Well, boiling point means we're going from liquid to gas. So a more compact state of matter to a more broken apart state of matter, right? So this is more condensed state of matter, right? They're closer together. And if we're going to spread things apart, that means we have to have a way to break apart those intermolecular forces. So if they're strong, it'll be harder to do so, therefore higher temperature. What will increasing intermolecular forces do to a melting point? You have to answer the question, what's happening when you melt? When you melt, you go from a solid to a liquid. When you go from a solid to a liquid, solid's even more condensed. Most of the time, solids are the most condensed state of matter. That means it's the same logic. So breaking apart an intermolecular force in a liquid to transition to the gas phase is breaking apart the same intermolecular forces that you would have to do in a solid to transition to the liquid phase, right? So when you melt something, you're not destroying the molecule, you're destroying the intermolecular forces. So melted water is still water, right? So increases the melting point as well. The tighter their forces are, the harder it is to melt it. The temperature will be higher. How about the vapor pressure? Sometimes we look at vapor pressure. I did that a lot in General Chemistry 1. And so let's remind ourselves what vapor pressure means. We have a closed container with a liquid, but we acknowledge there's some equilibrium gas evaporation. And the pressure of that gas is the vapor pressure. So my bottle of water here, with the closed container, has a set value for the vapor pressure of the water. So we just say increase because it all increases? No. Think about what's happening. If you're going from liquid to gas, if you have a strong intermolecular forces, and this is just happening on its own without adding heat. If you're going from liquid to gas, it's voluntarily breaking its intermolecular forces to be in the gas phase. That only happens, so the more gas will be produced, in other words, when there's weak intermolecular forces. If there's strong intermolecular forces, it's going to be less inclined to go to the gas phase. So in other words, there'll be less gas produced with strong IMF. If there's less gas produced, we have a lower vapor pressure. So this trend's the opposite, lower vapor pressure. One more really obvious bulk property is what we call viscosity. So we have these states of matter, solid, liquid, and gas, and you may eventually learn there's more than that because there's all those in between. I mean, like slime, right? What's going on with that? Or handling liquid, water, versus maple syrup or molasses. Those are very different liquids. Their flow is very different. And that's viscosity. Viscosity is a liquid that is resistance to flow. So if a liquid is slower to flow, if you pour two things down a funnel and one is very slow to come out, it's probably because it has very strong intermolecular forces. And it's just not strong enough to be a solid yet, but it flows. So something with lower flow, because of the stronger intermolecular forces, means that it has a higher viscosity. So it increases the viscosity. So just in case you don't remember what that term was, resistance to flow for a liquid. Okay, so some consequences in real life. First, I'm going to address one that we see in the lab all the time. We're always worried about solubility. And the universal solubility rule is really simple. Like dissolves like. Which is why in an organic lab, soap and water are not often enough to clean our glassware, because water is not organic. Organic molecules are very greasy. You need something greasy to clean the grease. Soap works okay sometimes, but oftentimes we use acetone. So we'll clean with water and soap, whatever doesn't come off just for environmental sake, we'll do a final rinse with acetone and collect the waste. So that acetone rinse dissolves any fine organics and also does a nice job of air drying it very quickly. It evaporates so quickly. We see this in everyday life, that like dissolves like. When you have in your kitchen something with two layers, like salad dressing. Everyone probably knew since elementary school about the oil and water not mixing. That's a classic one, but why is it not mixing? What is it about the oil that makes it not want to mix with the water? That answer lies within what's going on with intermolecular forces, right? So the water layer, which is what we call the aqueous layer. And in the lab, this is applicable to our extraction lab, versus the organic layer. We will always have those two layers. If we see two layers, we know one must be aqueous, one must be organic. What would drive something to occupy the aqueous layer? It doesn't always have just one thing. We could take oil and water, and then we could start adding things to the oil or water layers, and it's going to choose its layer, like food coloring. You could try that at home. Add some food coloring and see which layer it goes to. It'll tell you whether it's mostly a polar compound, which is what you see in the aqueous layer, or a non-polar compound, which is what goes to the organic layer. So some organic compounds are polar, the small ones with polar functional groups, like carboxylic acid. So acetic acid is polar enough to be soluble in water, which is why you don't have two layers in your vinegar that you buy at the store. It's vinegar, the acetic acid part, mixes with the water just fine. But when you take that solution and add it to some olive oil, you're going to have two layers, and the olive oil might have a compound that looks like that. It's a triacylglyceride. Big, long, greasy hydrocarbon chains. Yes, there's some polar bonds, but those effects are far minimized by the large number of hydrocarbons, which is why we call these sort of greasy hydrocarbon chains. So this is nonpolar. Thanks to these greasy hydrocarbon chains, nonpolar chains. Whereas acetic acid, it only has a little methyl coming off. That's its nonpolar part. The rest of it's polar. Water, as we know, is polar. So has no problem. These are all soluble with each other or miscible. So if we say something's miscible in the aqueous layer, it's probably polar. If we say it's miscible with the organic layer, it's probably nonpolar, right? It must be. So I want you to think about the salad dressing analogy whenever we're doing our extraction discussion, our technique for lab, because we'll have what's called a separatory funnel, and we'll be intentionally pouring things in and use extraction as a separation technique. Oftentimes, but not always, the organic layer is on top, but that's based on density. And so that's our aqueous layer. And so we could start off with something like pentane on top, water on the bottom, and then we could just start adding molecules and we could see which layer they go to. Or we could take something that's a mixture, which is the more common reason to do an extraction, and add, if we know something has both properties but would like to be in the organic layer more, if we add the organic layer to it, it would pull it out, extract it out of the aqueous layer. Another sort of really common everyday life sort of application of this like dissolves like is the whole concept of fat soluble versus water soluble vitamins. So this got chopped off. This is vitamin C. You might have been told that one of these vitamins you have to be careful not to overdose on, and the other one you don't have to watch the dosage so carefully. That's because one's fat soluble, one's water soluble. The fat soluble ones can accumulate in your fat, and the water soluble ones can come out in the blood and urine quite quickly, be metabolized. So let's make a prediction. Which one of these, in case you didn't know already, which one should you not accidentally take 2 pills of? Okay, so which one's fat soluble, in other words? Fat soluble. So in fact, and that's because this is very polar. Look at all those carbon-oxygen bonds. I mean, every carbon has an oxygen. So except for, oh yeah, even that one. So every bond, every carbon has a polar bond. So this is polar. So that's in the blood or urine, which is mostly aqueous. That's your aqueous layer in your body. Whereas the fat-soluble vitamin, it's only one polar group, this tiny group here, polar. The rest is nonpolar, highly nonpolar. So if we had to judge how this molecule behave, it's going to act like a nonpolar molecule overall. So that means it's going to go in the oil layer. Where's the oil layer in your body? The fat. Okay, so greasy. That's why we use the word greasy for these. Grease is made of hydrocarbons, literally. All right, so that concludes our review. But I understand it's not all review if it's been a while. So this is review in the context. This is what we got from general chemistry, hopefully, that we need to know again. But we spent hours on it, so don't feel bad if some of it's not completely review. Go make up for that now and do the homework, because from there on, it's very new. And it'll feel like we hit the ground running with that when we start that. So make sure you're caught up and ready to run, okay? All right, see you soon.